All right, I started week 3. Good to hear the rumblings of people who aren't asleep. That's one of the perks of teaching at 12 instead of teaching at 9. But I don't know, people look a little bit defeated. Like they have that mid-quarter look to them. How's it going? We feel okay? Are we alive? Awake? We're dying. Surely. As George Carlin says, death is caused by swallowing small amounts of saliva over a long period of time. I don't know if we have a counter proof for that or a counter evidence for that, but it shows that what is asserted without evidence can be refuted without evidence.
Water poisonous just takes 60 to 100 years.
Yeah, exactly. You need it to live, but it will kill you.
Kill you a lot quicker. If you just have 3 gallons in the space of an hour and you're perfect.
I was gonna say, yeah, you're getting it.
Yeah, if you want to dilute your blood.
Right. So this week is an important week. We have a deadline tonight for homework 2 if you'd like to get feedback on it before we take our exam on Friday. The grader is, I just checked in with him this morning, a bit behind. So we'll see what happens for the next couple of days. May have to bring in my whip, we'll see. But we'll get as much of this turned around and back to you as soon as we can. If I become concerned about the level of feedback that you have ahead of the time to really study for the exam, keep in touch with me about how you feel about that on an absolutely as needed basis. If the grader is unable to do that, maybe we do something like try to push the exam a little bit. I really try not to do that because I like to, at the beginning of a quarter, identify what those important dates are going to be and then not change them, because as soon as you change them, then people have said, well, I designed my schedule around this, my flights around this, my whatever around this. And if it's my fault for changing it at the last minute, I don't like to do that. So I would like to do this on Friday, but obviously I'd like you to be able to put your best foot forward and feel like you know what's happening in this class and feel confident about this material before I put an exam in front of you. So there's that, then we have a review session on Thursday and our exam on Friday. So that is still the plan until I have evidence to the contrary. I trust our grader a lot. We'll see if that trust is well deserved or not in the next couple of days. Anyone have any questions about schedule or any content that we've covered ahead of diving back into the pumping lemma? What has a weekend done to your view of the pumping lemma? Do you feel like I barely remember what happened, it's all a blur? Or is it I kind of remember it and with a little refresher, we'll get there.
All right. All I know is you have to pick an abstract possibility where there's no way you can make a proper DFA out of that logic.
It's a good start.
Need some practice proofs.
Yeah, so this is a proof by contradiction. So let's go through the basic idea before we dive back into where we were last time. So let's actually give you the.
Oh yeah, I remember the game.
Yeah, we had a game. Here was the example that we fully went through. We said there are 2 really important rules. We said that the length of XY, whatever this breakdown happens to be, that has to come within the first M characters. Recall that M is the number of states in the associated DFA that exists for this language. Since this is not a regular language, no DFA exists for it. But if someone were to assert that this is a regular language, then you could say, okay, well, if it is a regular language, then how many states are in the accepting DFA? If they could tell you that information with M, your task as player 2 in this game now would be to pick a string form that adheres to that language. So we said A to the M, B to the M, B to the M, A to the M, adhered to WWR. When you pick that string and instantiate it with M, whatever player 1 picked for the number of states that are in the accepting DFA, the way that you can prove this is to say, all right, well, we have this string, A to the M, B to the M, B to the M, A to the M, that is in WWR. As we do this, we note that the first M characters are all A's. What we know about any DFA for a language is that if m is the number of states, by the time we have read m characters into the string, we have either exhausted, we've visited every state exactly once and looped back to some state that we've been to before, creating a loop, or no such DFA exists. Those are our two options. So by coming up with this string type, a to the m, b to the m, b to the m, a to the m, you've allowed yourself to now be able to show that this completion of a loop, there is a loop completed within the first m characters, they are all a's. Which means that we can get to that loop, complete that loop, and get to a final state. Great, that is X, Y, Z. That is that breakdown of X, Y, Z. Getting to the loop, completing the loop, and getting from the loop to a final state. We know that X, Y has to come within the first m characters. We know that Y has to be at least one character for that, the size of that loop. The loop can't consume 0 characters in the input. That doesn't make sense. With those two constraints, we can now show that, all right, within the structure of that associated DFA, we can get to the loop, iterate the loop again, and get to a final state. And that needs to also adhere to the language, because this DFA, this abstract DFA, accepts all strings in A to the M, B to the M, B to the M, A to the M. Except that when you loop this twice, you show that all you're doing is pumping extra A's in the front of this string. If you pump more A's at the start of the string, you have A to the M plus some K, B to the M, B to the M, A to the M. So if you want to really show this, I think that you can, as part of your proof, say something like this, where all you've done here is pump K extra A's into the first part of this string. And you can show that as long as K is greater than or equal to 1, which is necessary, because if you're going to pick an I that is not 1, like I equals 2, you're repeating this Y one more time. So the length of Y, we can say that K is equal to the length of Y in this case for I equals 2. And since we know this has to be at least 1, we know the value of m plus k here is greater than the value of m here, or m here. And this string now breaks this language and breaks this language in such a way that we've generated a string by the definition of a DFA that player 1 gave us that was supposed to accept this string. We came up with a counterexample of a string that their DFA has to accept that cannot be in the language. Yeah.
How are we picking M? I know in this sense, it's like an indeterminate amount of states because you're
Yeah.
repeating it.
Yeah.
So is M just pulling that out of thin air on every?
M is, if we're making our argument, the only time M gets instantiated is in this game, which we said is not fully representative of a proof. So we have to go through it. That creates an algorithm that says whatever player 1 picks for M, we're going to instantiate in this string as A to the M, B to the M, B to the M, A to the M. I again forgot to make this change. That should still be there. It's not. But whatever they pick here becomes what we do here. And it gives us kind of a ground to reality in a way that if I just carry M through the whole thing, it just seems like it's a really arbitrary argument. If you make it a game and allow player 1 to instantiate M, then the real proof is saying no DFA with M or fewer states exists. So yeah, if we instantiate M, we're not making a complete proof or a complete claim. So we have to carry M all the way through our argument to make a general argument of why this is complete. But if you're playing the game, put the onus on player 1. You need to pick an M and come up with a DFA such that you can show that this language is regular. The idea is to show that player 1 cannot win the game via any instantiation of M. It's impossible for player 1 to win the game. There. Questions? Hopefully that helps as a refresher to where we were. So we were in the middle of another example from here to show kind of how this process works. And we will get through these examples some actual drawing out of a real, what does a proof look like for this? So we wanted to come up with the reasoning for why a language with all strings with more B's than A's is not regular. Intuitively, this was because we need to count the relative number in A's and B's that we've seen as we parse the string. So maybe we have some string that is A, B, 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 A, B, A, B. 2, 3, 4, 5, 1, 2, 3, 4, 5, B. Now it adheres to those rules. As you're parsing this, you need a single piece of storage. If you were writing a program for this, you would just keep track of some integer that is the number of more A's than B's, or number of more B's than A's that we've seen as we read each character. So I'm going to say the number of more B's than A's. That's what this represents. And you just read an A, and now there is -1 more B's than A's. You read another A, and this becomes -2, -1, 0, 1, 0, -1, and 1 again, 0, -1, 0, 1. And because this finishes with a value that is greater than 1, then we would accept the string. We can see that with a single piece of memory, a single variable, we can now determine whether an arbitrary string is in this language. But because this is regular, regular does not allow for any working memory. We can't actually go show that. We need a way to prove that there is no algorithm that exists without this storage. Can we, with a single pass through this string, determine whether there were more B's than A's based on just a state machine with no history? We don't get to see when we're at this A, we're distinct from being at this A. Because here we've seen more B's than A's ahead of this, but here we've seen more A's than B's ahead of it. How do we distinguish in a state machine or a grammar the difference between being in those two states, where the history is different? We can't. So to show that it's not regular, we go through this exact same pumping lemma. And at the end of Friday's class, we came up with a very good choice for our W. We had a really good example of this. Can someone remind me of what that was? I remember, but I want someone else to remember too.
A to the M, B to the M plus 1.
Yes. So we said we're going to set a choice for W as A to the M, B to the M plus 1. Do we agree this string has more B's than A's, regardless of what M happens to be? You can instantiate M with any value, and this string is in that language. By doing this, remember that the other rules we had, we said, were for any DFA for this, we know that since this language is infinite, that there's a loop somewhere in the DFA. Regardless of the finite number of states of the DFA, because there are an infinite number of strings in this language, we need some loop in the DFA to be able to pump some number of times to create that infinite number of strings. So to do that, we're just going to allow us to say, all right, the length of xy, we know this is less than or equal to m, and we know the length of y is greater than 1. The two things greater than or equal to 1. We know both of these things to be true. They have to be for any DFA that accepts a regular language. By allowing us and making this string as the option, we're basically, if we're going to draw out that line of what we saw before, of what the characters are, we're going to have some number of A's up to our mth character, and then we're going to have some number of B's that is another m plus 1. So we get up to 2m plus 1 in terms of the total character count of this string. And that's just generally how this string is going to be built. But we know that when we transition from seeing A's to seeing B's, we need to have seen X and Y. We need to have gotten to the point where we've started a loop and gone back to somewhere that we've been before, completing a loop by the time we've reached all A's, or by the time we've reached the end of the A's. This says that if we were to repeat this loop some number of times, we would be pumping only A's, and you would get something like A to the M plus K, B to the M, such that K is greater than or equal to 1, because this represents, if we're just saying I equals 2, this would be the length of Y, the exact same argument from before. Since This needs to be +1. Since this plus k is at least this +1, the end result of this is regardless of what the value of k is, 1 or greater, this string no longer has more b's than a's. So by iterating that loop at least one more time, we've generated a string with more a's than b's or an equal number of a's and b's, neither of which is in the language, and that becomes what you latch onto for your proof. So we came up with exactly the string that I had planned. We knew that the loop is all a's, which means that as we pump that, the resulting string cannot possibly be in the language. We end up with eventually more a's than b's. There's nothing that says that I has to be 2. You can pick some very extreme value of I, like 10,000. Just to be able to show it as an example, let's say if we instantiate this k to be some arbitrarily large number, according to this DFA, that string should still be in this language. It's obviously not. So let's actually write out the language for this. So you would start out by saying something like, great, this is going to be the information that's given to you. You know what the alphabet is, we'll call that sigma. We know what the language is, we'll call that L. So you would start by saying something like, assume L is regular. Therefore, a DFA with a finite number of states exists that accepts it. So this would kind of be how you start your proof or you set up your proof. We know what L is, the language of more B's than A's. According to the alphabet of just A's and B's, we assume it's regular. We know that every regular language has a DFA with a finite number of states that accepts it. Great. We're going to move forward with that DFA, whatever it happens to be. I'm actually going to put M in here because now we're defining M as the number of states in the associated DFA. From here, we latch on to this idea saying that we want to be able to accept some string type. You say, let W equals A to the M, B to the M plus 1, a you say we've now defined W to be the W that we've picked as player 2. Then we just further say that this is a sentence in the language, which makes sense. We know that M is the number of states in the DFA that accepts it, so now we can just state that this is a string that is in the language. Now we can refer to this by W. Next step, we move on and we say we can break down W into components. So ST here just stands for such that. Let W be broken down into components X, Y, Z such that the length of XY is less than or equal to M and the length of Y is greater than or equal to 1. I apologize, my handwriting is garbage today, apparently. So we break it down into those components. You can say something like, according to W as defined above. According to W as defined above, X and Y must consist of all A's. We can now pick a value for I. We can say, we know that X, Y to the I, Z must be in the language for all I 0 or greater. We've now broken it down and showed that X, Y, Z produces A to the M, B to the M plus 1. But we know that X, Y is all A's, and we know that the length of Y has to be greater than or equal to 1. So if we pump I equals 2, we are adding at least one Y that I equals 2, put down 1A to A to the M, B to the M plus 1, giving us A to the M plus 1, B to the M plus 1, which is not in the language. And then you would just terminate by saying something like, therefore, this DFA does not accept L and cannot exist. Since no DFA exists to represent this language is not regular. And that's how I would finish this off. But I think that just seeing some set of logical mathematical reasoning here, this is kind of the outline of exactly what you want to do for any kind of pumping lemma proof. Unfortunately, this is as easy as it gets, and some of them get to be harder than this. Why it's harder is because you will end up having to show this in cases, because you won't have a single line of reasoning that works for the entire language. So you have to split it up into this language is a concatenation of some additional languages. I'm going to go through a different value of I for each of them to show you that none of these will work for each of these cases. We'll get an example of that in a bit, but I just want to give you that basic, it's not basic, but the baseline, I guess, set. So assume the language is regular. If a language is regular, it has DFA. A DFA needs to be able to represent every single sentence in the language. So you're going to come up with a sentence form that allows you to go through the rest of this. We came up with a sentence form, A to the M, B to the M plus 1. Running with that, break that example down into the X, Y, Z components based on the rules of what we know about X, Y, and Z. Based on the DFA needing to loop back by the time X, Y is done. We know that that happens before the mth character, M being the number of states in the associated DFA, Y being the length of the loop. We know that X and Y now have to be all A's, so we can pump it some number of times, giving us an end resulting string that, according to this DFA, which accepts this language, the DFA accepts this string. I guess I should say something like, but is accepted by the DFA. Therefore, this DFA does not recognize this language and breaks our assumption. We reach our contradiction. A DFA exists that represents this language, but that DFA can't recognize the language. There exists at least one string in the language that this DFA accepts, or sorry, a string that's not in the language that the DFA accepts by the definition of that DFA. Therefore, the DFA can't exist because contradiction. We've proven that a DFA that only recognizes the sentences in this language exists, and also that it accepts a sentence outside of the language, which is not what we set out assuming. Based on that contradiction, this language cannot be regular. How are we doing? Somewhere in here. This is something that definitely needs a lot of repetition and a lot of practice. Maybe I can see a show of thumbs at the moment of how intuitive do this sequence of steps seem like it solves this problem, or that it asserts what I'm saying that it asserts. Is that, do we buy this and understand it? Do we kind of, sort of, maybe a little bit, but not really, and no idea what's going on? So we're somewhere between here and here, mostly here. Okay. Kind of what I would expect at this point. But let's at least, yeah, question?
I just want to make sure I'm reading this correctly. It's
Yeah.
the fifth line from the bottom, it's, the Y, is that less than or equal to 1 in the middle?
Yeah, greater than or equal to 1, sorry.
Yeah, greater.
Yeah, length of Y is greater than or equal to 1, looks like a 2. Greater than or equal to. It's probably not something I want to half-ass my second grade level of handwriting on. Other questions?
Sorry,
Yeah.
I don't understand the last part where it says like, giving us a to the power of n plus 1.
Yeah.
How do we get that if I equals 2?
Yeah, so let's say we have this DFA, and I'm only going to draw the relevant parts of this DFA. So we get to some middle point, and then at some point we go back to some state that we've seen before, finishing off this loop, basically. So we get to this point, and this state is final. So here is our x getting there for the first time. Here is our y that is the definition of the loop from here back to here. And then we have some path to a final state. Do we agree that x, y, y, z is in this language accepted by this DFA? We get here, we iterate the loop twice, and then we go to the end. According to this DFA, that's in the language. So if we do that for this W, such that we have m states in this, we've said that the string that we are using is twice plus 1 the length of that number of states. So regardless of the number of states, we blow up our string to be the appropriate size. If someone says there's a 10,000 state DFA that accepts this, the string we're using is 20,001 characters long. We go through this point, and now we just say the I equals 2 is the number of times that we're doing this loop. If we just did xz, that's a sentence in the language. xyz is a sentence in the language. xyyz is a sentence in the language. We can iterate this loop an arbitrary number of times. But if we come up with an intelligent value of this string w, we can then pump it, saying we're going to do this loop twice, 3 times, 4 times. We use twice in this argument, just saying that at the shortest this could possibly be, the length of y is between 1 and m. That's kind of the bounding points of y. The loop has to be at least 1 character long, and the longest it could be is go through every single state in the DFA and go back. Can't possibly be longer than that. So we're adding some number of values, some number of a's here between 1 and m. So I like to use k here to just say this gives us a to the m plus k, where k is between 1 and m. And even its lowest value, 1, A to the M plus one, B to the M plus one is not in the language. There aren't more B's than A's when there are the same number of A's and B's. Does that help? Does that make sense? Ready for another example? Maybe trying one on your own? Let's see how far we can get. Everyone have everything they need from the board? Here we go. The language you want to show, AB to the N, A to the K. Constraints on these, N is greater than K and K is greater than or equal to 0. First place we want to start is intelligently selecting W. And I will argue that this is usually the hardest part of this whole process. Is coming up with what is the string form that is going to show this well. How can we turn this form into either something we've seen before or something with an obvious pump at the beginning of it that's going to create something that is out of the scope of this language? And remember that we want to be using the variable m in this string. So don't pick a finite length string, pick a variable length string based on m, the number of asserted states in the DFA that accepts this language if it's regular. Yep.
Because we can distribute out the n, we could do something like A to the m, B to the m, A to the m plus one.
That
Or
will
is that
not
shallow?
be the AB to the n, so it's some number of repetitions of A followed by B. We're gonna get AB or AB, AB, or AB, AB, AB. So we can't do something like A to the M, B to the M, because that will not be in that language.
Yeah. Plus one.
Our loop,
Exactly.
our loop
The
Y
exact
has to be a B at some.
So what's being asserted as a good string is AB to the M plus one, A to the M. Does this adhere to those constraints?
Yeah.
Yes. What do we now know about the start of this string, the start of this DFA? We know that the loop has to come within the first m characters. And we know that this is twice plus one as long as that. So we know that the loop is happening in some sequence of A's and B's. We're never going to see A's in a row by the time we reach that loop and iterate that loop. How can we use that idea as the baseline of a proof?
Can you say that one more time?
Yeah, so AB to the m plus one, if we're drawing this out as a sequence of characters, we have A, B, et cetera, and this is going to end by the time we get to the length of 2m plus one. So we know that by the time we get to m, all we have seen is A's and B's. But we don't know whether it ends in an A or ends in a B. That's what we don't know, and that's what's going to create a little bit of a headache for us.
That's the 2m plus 1.
Yeah. Yeah, I gotta just write bigger. Because if you have AB to the m plus one, sorry, it's 2m plus 2.
Alright, why is it 2m plus 2?
Because this, we're doing AB, which is 2 characters to the m+1, so how many characters have you consumed by the time you're done seeing A's and B's? 2m+2. The important thing is the terminating M character here. That says we're only gonna see sequences of A's and B's. So legal places M could end is something like AB, 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 something like this. This could be the start, the ending point of M. If we asserted that there were 6 states in the DFA. It could also be something like AB, AB, A, if we asserted that there were 5 states in the DFA. This is still part of the way down that AB, 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 even though we haven't completed one iteration of AB. If we assert that there are an odd number of states in this DFA, we're gonna see this string ending in an A. What does the loop look like? We know that it's possible for the loop to start with an A and end with an A. We know that it's possible for the loop to start with an A and end with a B. Could it start with a B? It can't. So it could start with a B and end with an A, start with a B and end with a B. So imagine that there's some DFA that exists. We see an A, a B, an A, a B, and at some point, this loops back to itself. Where that loop starts or ends will determine, so we could do something like go from this state back to this state. So X is A, Y is B, A, I don't know, you can't make something here. If it's A, then you get 2 A's in a row. If it's a B here, you get 2 B's in a row. But maybe this goes to some other state out here that goes back here. So this would be a B and then an A. So now we have an X that's an A, a Y that is B, A, B, A, and then a Z that gets you to the final state. You could also put this after here and make this an A and make this a B. In a way that now this loop still starts with a B, but now ends with a B instead of an A. If this now goes back here instead of there, now it would end with the opposite characters. So we really have 4 cases here of starts with an A, ends with an A, starts with a B, ends with a B, starts with an A, ends with a B, and starts with a B, ends with an A. Can we combine those states into one piece of reasoning? Or do we have to tackle each one of those cases? You can imagine now that we need to split this into, you hopefully don't have to do this, but sometimes we will have to, into the 4 cases of, all right, there's at least one loop in this DFA. If that loop is of this form, then logic follows such that pumping it some number of times shows something that's not in the language. If we go down this path, logic that shows not in the language, depending on the associated path of what that loop entails. Yeah,
Only one of these cases has to fail.
all of them have to fail.
They all have to fail.
Yep. Because otherwise, some DFA could exist, a DFA of that particular form. If we can show that none of them exist, none of them can exist.
I'm a little lost here because
Yeah,
I did it backwards. I did it A, B to the M, and then A to the M minus 1.
Okay, yeah.
Because you're looping in M.
yep,
and I
that
have
still
M.
works. Because the string, the other constraint that we talked about is the string that you want to pick is at least length M. And yeah, that will work because you're still in ABs here. So you could still do something like AB to the M over 2, because then you've still consumed M characters that are seeing only ABs, but you wouldn't want to put anything here that is AB to the M that's less than AB to the M over 2. Then you have the extra case to consider of, well, there are all A's at the end, we could pump those. And that would break everything. We could show that such a DFA could exist if we did that.
that what is class is sort of degree for, because you have to check every W that we choose.
The entire logical process of what you outlined. And I'm the kind of person who doesn't like to say, there is one path and only one path, learn it and regurgitate it. I want to say, there are lots of ways to do this, do it the way that's most intuitive to you. And then the onus comes on the grader. You know, understand what this person is trying to do and state,
But that's not.
and check how complete it is. How are we doing? Came up with a good string. We know that X and Y have to come from this part of the string. These 4 cases are actually only 2 cases, thankfully. So this becomes a disgusting amount of work if you think of every possible case sometimes. It'll serve you well if you can think, is there a way to condense this down into fewer cases? Because these cases are actually equivalent to each other. The logic that flows from case 1 is the same as the logic that flows from some other case. So let's break this down just a little bit. The logic will line up with, all right, if Y is a single character that is A, we can choose I equals 0. If we choose I equals 0, then what happens is we're removing an A from the string. If you remove an A from anywhere in this string, it now either starts with a B or it has consecutive Bs, neither of which are allowed in the language. On the other hand, if Y is AB, we will choose something like I equals 0. Again, violates the n is greater than k clause. If we remove an entire AB from this, then we violate the clause that n has to be greater than k. We have an equal number of AB to the m and a to the m, because we removed one AB. And we do just have to continue this. I said there were 2, I actually lied. There are a few more than this, but now you have to think of, all right, how could this change? What are all the possible cases for Y? It could be BA. It could be BAB, ABA. How do those neatly split into cases that you could make an argument for?
Let's call it A to the N. To cover all.
Yeah.
Infinite lengths of the loop.
Yeah. So I think breaking it into those 4 cases will actually help. Starts with an A, ends with an A, ends up being exactly the same case. If you said I equals 0, you're removing more A's than B's. Since we know this AB to the M has to contain the same number of A's and B's, if you're removing more A's than B's or more B's than A's, then it cannot possibly adhere to that structure. On the other hand, if it starts with an A and ends with a B, or starts with a B and ends with an A, you can kind of combine those in that we're going to be removing some number of ABs from the language, which is going to be violating the n is greater than k clause. And as the length of Y scales, you're just removing more and more and more, which does not change the underlying assumptions that we're making. We're just removing more characters and making n lower and lower and lower, which can no longer be greater than k. You were right on the boundary based on what we had already chosen. So setting I equal to 0 instead of 2 or 3 or 4, saying we don't go through this loop at all, shows that this is actually really fickle. You don't want to choose I equals 2 or 3 or 4 here, because getting more cases, more A's and B's in here doesn't actually break this. It still adheres if we say AB to the n plus some constant c, AB to the n plus c, a to the k. N is still greater than k if you pump more of this, because what we started with had to adhere to the language. So the end result will adhere to the language. So recognizing that we need to take something away here and not add something is another key insight. To give you a sense of levels of complexity, something like this would be a massive challenge problem on a homework. Something that I think you could do given enough time. I would never throw this on an exam. It would take the best of us probably close to an hour to just get through all of the cases and represent all of that. And I would have way more to ask you on an exam than just that one question. So throw out something with cases, especially cases that are this complex and this many, from what you're preparing for exam 2. Again, this is beyond what we're focusing on for exam 1, but for a homework, I think this is a really good challenge exercise. And of course, I'd be more than willing to help you put it together, assuming you come to me early and ask questions. Questions on any of this logic, how this breaks down into cases, how any of those cases could be shown? I didn't go through the entire thing here, but I can if there's interest, or if this is something we want to come back to. It's easily something we can come back to ahead of having an exam on this, because that'll be a little ways out.
Would like to see how you got it down to 4 cases, like how you way of thinking.
Yeah,
Because in my mind,
What would the case of quiet close be look like?
so yeah, the case for, I would actually break it down into the 4 cases. Starts A, ends A, starts A, ends B, starts B, ends A, and starts B, ends B. So a single A is a starts A, ends A. A single B is a starts B, ends B. And now any possible value of Y falls into one of these 4 cases. So for a single B, if we're in A, B, A, B, A, B, A, B, A, B, et cetera, then this case breaks down into this string will be removing one more B than it does an A. If it's just B, then the number of B's is 1 and the number of A's is 0. If it's B, A, B, the number of B's is 2, the number of A's is 1. And this has to, in order to end with a B, always have 1 more B's than A's. So since this is coming from this first part of this, there's no way for even this to leak into a bunch of A's at the end. So we know what follows this is A, B, et cetera. And what comes before this is at least 1 A, because it has to start with an A. So maybe we had a state that led to a loop, and then we can iterate this and call this our loop, and then get to termination somehow via this followed by some number of A's. If we remove more B's than A's, we know that AB to the n has to have the same number of A's and B's. So that means either there's going to be 2 consecutive A's after we remove this segment. There's an A that comes before this B, and there's an A that comes after this last B. Shorten that, you either get AA, or if, and I guess that's the only thing, that's a complete argument, because there's no way this B leads to a bunch of A's at the end, because M comes before this 2M plus 2, where we're going to be terminating these A's and B's. And that's true regardless of the length of this loop. More B's than A's, you take that loop out, you get consecutive A's. Done, violates the language. Can't have consecutive A's and then go back to A's and B's. How we doing? We look defeated. I think we all just need more caffeine. It helps everything.
Might need to come in to like
It
ask.
helps with the dopamine, but it doesn't help me understand it.
Yes, that is what office hours will be for. I am hoping that I'll be seeing whoever could use an extra push with this, and I expect that to be everyone or almost everyone. Because this is not easy. I'll be the first person to admit it. Not easy. but it's incredibly important to the concepts of, the underlying concepts of this class. We need to be able to show a language is irregular as part of building a compiler. We need to be able to show whether we can tokenize, come up with words or elements of meaning, components within a stream of characters. I have class at 2 today, so I will be there for the hour. Tuesday, Thursday, Friday, I'm kind of there as long as I need to be. But Monday, Wednesday, I have class from 2 to 4:30 and I'm kind of short. Okay, I'll see you for that.